Hi folks, welcome to the fundamental theorem of calculus, putting the fun in fundamental. This is arguably the most important section of calculus, maybe of all three sections of calculus that you're going to take, some of you might take. This fundamental theorem of calculus is kind of the foundation for Calc 2, and then comes back again in Calc 3, and you see it in different forms. So it's certainly fundamental to your study of calculus. All right, so let's dig in. Let me define, first of all, this idea of an area function. An area function is just a function that gives the net area of a region bounded by the graph of some function, and the t-axis, which think of the x-axis, I'm just using t as a dummy variable, between some starting point a and some ending point, which is going to be our variable. In other words, that endpoint can vary. So a of x, that is the area based on x, is the definite integral between a, little a, and x. So t here is just kind of holding the place for what we used to think of x, but now x is moving. So as a quick example, this net area function for this is a function that tells us the area from 1 to whatever value we land on. But keeping in mind that it is net area, meaning it's going to start losing area, or we're subtracting this area where the function falls below the x-axis. So our definition then is for a continuous function f and some t value greater than our starting point on our interval, the area function is this definite integral from a to x of our function. So x, keep in mind, is our variable that our area is being determined in terms of. So we want x to always be greater than or equal to a. So the area function gives the net area of the region bounded by the graph and the t-axis on the interval a to x. So think of it as time, or just think of it as the old x-axis. It's just a dummy variable to hold our place because the thing that's moving now is x. So this is the graph of this is the function that we just looked at the graph of, negative 0.2x squared plus 1.5x plus 4 with a left endpoint of 1. And the area function with the left endpoint 1 is just the function that would tell us what the area is. And what we saw from the definition was that that is the definite integral from this starting point 1 to whatever x value we land on. So for example, the area function at 5 would tell us how much area is in this shaded region. The area of, if we plugged 15 into the area function, it would give us the pink region up here minus the black region down here. So whatever number we land on, that's what we plug into x in our area function. Alright, so let's look at this a little more in depth. I want to consider the function 1/2 t plus 2, just a straight line polynomial function. And the area function is 1 to x of that function. So starting at 1. So notice this is going to give us the area of a trapezoid between 1 and some value x. Alright, so let's make that some value that we end at, let's make it 4 to start out with. Well, I'm going to cheat and use the idea that we know this is a trapezoid. And we can look at the graph of this just to be sure. It's this. And my function is going from 1 to some other value. So for this one, for this problem, we're going to go from 1 to 4. So 4 is the x value that my area function is going to end at. Alright, so knowing that this is a trapezoid, let me find and I know the area of a trapezoid is given by 1/2 base 1 plus base 2 times the height. So base 1 and base 2 in this case are going to be the height above 1 and the height above 4, not to be confused with the height of the trapezoid, which is actually just the way the trapezoid is laying. It's going to be 3. So my base 1 could be the height above 1, so the function value, and the function value of 4. And we just said the height of that trapezoid is 3. So of course you have to tilt your head 90 degrees to see it in that way, where the height is 3. Alright, now we can figure this out pretty easily. F of 1, just plug 1 in for t, and you get 1/2 plus 2, which is 5/2. Plug 4 in for t, you get, what, 2 plus 2, which is 4, and then we have times 3, so quick arithmetic here. What is that, 8/2, 13/2 times 3. This is all going to be 39/4. Alright, so what if we wanted to do that for just any old x? What do we get? Well, same idea, 1/2. 1 stays the same because on my graph, notice, x can just be anything, but the 1, because that's what we chose our area function to start at, 1 stays fixed. So then the other one, the other height of my trapezoid is whatever x value we end at. So that is a of x. We plug that in, that's a of x. And here we figured out a of 4 in the last example. Now the height here is whatever my x value is minus 1. So in the last one it was 4, but in this one it can be whatever x we end at. Okay, let's see what we get. Now f of 1 stays 1/2. F of x, well, that's easy enough. That is just the function value with x the function with x plugged into it. Alright, times x minus 1. Alright, let's simplify things a little bit. Let's see, I can add the 5/2 plus 2 to get 9/2. So that is 1/2 x plus 9/2. X minus 1. And I don't know, maybe I don't like fractions in there, so let's pull a 1/2 out. So we have 1/4 x plus 9, x minus 1. Foil these guys out. X squared plus 8x minus 9. And then multiply that 4 back in, maybe. 1/4 x squared plus 2x minus 9/4. So now what that says is if I plugged 4 into here, I should get what I got originally. So let's try it. Just as a, call this a check. 1/4 times 4 squared plus 2 times 4 minus 9/4. Well, that's going to give me 4 plus 8 minus 9/4. So, well, of course, this is 12, and 12/4 is 48/4 minus 9/4 is 39/4. Looks good. So now if I wanted to know what the area was if that x extended to 5, I can just plug in 5 into my area function. Now there is, if you look at what our original function was, 1/2 t plus 2, there is a connection between these two. And I'll draw that connection more definitively in a minute, but see if you can recognize it. Okay. If not, hang tight. We'll get there. So now let's try to find an area function for this guy. Now, of course, I can't use the fact that I'm dealing with trapezoids anymore, but I know something about an area function. We know that it is the definite integral from 0 to x of my function. So, definite integrals, oh, and you know, I should be more careful. Let's use a dummy variable here. Okay, I know how to deal with definite integrals if we go back and look at the limit definition of our Riemann sums. So I need sum of k from 1 to the number of rectangles of my function times delta x. So this is just back to the previous section that we learned about definite integrals. Now the tricky thing here is that in the previous section, I was going from a single number to a single number, and that helped me figure out what my delta x is. But now, notice what I have, and I really am being very not careful. Let me do t sub k and delta t. So my delta t, which is taking the place for delta x, I just want x to represent the variable in my area function. So delta t was these two endpoints. So in this case, x minus 0 over the number of rectangles that I have. And my t sub k that I'm going to plug in, so of course this simplifies to, in this case, x over n. And my t sub k, well, that is the starting point plus, and if I'm doing the, assuming I'm doing the right Riemann sums, k delta x's, or in this case, delta t's. Okay, so with that information, let me figure this limit out. So my f of t is my f of this, which means I'm going to square those, because we're dealing with the function x squared. So k x over n squared times delta x. Okay. So now think about what is a constant with respect to this summation. The n is still constant. The x is constant with respect to the summation. So I can pull out, I'm going to skip a couple steps here because we've done this a few times and hopefully you've been working on several of these problems. But I'm going to pull out an x squared and an n squared, and then also the x and the n. So that is really x to the third over n to the third, and I'm left with summation from k equals 1 to n of k squared. And then for the limit, notice the n is the only thing that's changing, so x is actually a constant with respect to the limit. So I can pull that out. Limit as n goes to infinity. I don't know, looks like I've been writing 0. Let me change that to infinity. The number of rectangles is going to infinity. It's the delta t's that are going to 0. So here I have 1 over n to the third. This will just help ease the make things look better as I do my calculation. And then the summation of k squared we know is n plus 1, 2n plus 1, all over 6. All right, so FOIL that top out, bring the n to the third in. You've got, as n goes to infinity, of n, 2n to the third plus 3n squared plus n over 6n to the third. Now, if you break these up and take the limit, the only thing that'll be left, or if we just think about taking the limit of the rational function, you'll see that you're going to be left with 2 over 6, which is 1/3. So this whole thing becomes 1/3 x to the third. Now, see if you could see the connection between this area function and the original function. And if you see it, that brings us to our first part of the fundamental theorem of calculus. So if f is a continuous function on some interval a to b, then the area function, which we're going to call a of x, is the definite integral from that little a, the start of our interval, to x of our function, f of t dt. So, if f is continuous, then the area function is continuous on that same interval, and it's differentiable on the open interval, a to b. And what we get is that the area function satisfies a prime of x equals our function. And that is a big deal. And so we write that as the derivative of our area function is the derivative in terms of x of that definite integral, and that will equal this function. So what this means is that the area function of f is an antiderivative of f. And what we have just done is we've connected differential calculus, all those derivatives, with this idea of an integral or an area function. That is really, really big. And if you don't see it, you'll see why this is very useful to a first-year calculus student in a second. Okay, let's prove this. So the reason this is true is if you think about, let's take the area function at some point x, but let's move a little bit further. And we subtract the area up to x. So for example, what this looks like is you've got some area function which starts at some starting point, a, little a. We calculate up to some point x plus h, and we get that area. But then we come here and we subtract the area up to x. You're left with this area. So that's the area that we're talking about here. And notice this distance from x to x plus h, that is h. So if you think about it, this area, I kind of drew it in a box, that's approximately, and let me write approximately, the function value of x, about that height, times h, which is the distance from x to x plus h. Alright, so h, if I move h to the other side, that is divide, then we get this approximation. Alright, now if I throw a limit as h goes to 0 on both sides, we'll notice the top here goes to ax minus a of x, which is 0, and the bottom also, of course, goes to 0. But really what you should notice is that this is the definition of a prime of x. And what we're saying is, really at this point I don't need to use an approximation because we're talking about the limit, and once we've taken the limit, these become the same. Now the reason, if you think about what's happening on the right as h goes to 0, well, there's no h involved here anymore. So as h goes to 0, f of x doesn't change. F of x just stays f of x. And so what we've shown is that the derivative of our area function is the function itself. I shouldn't say the function itself, the function that we're interested in. All right. So if you look at my slides, I've basically written that same thing out in the same steps. Okay, so if I wanted to calculate this integral, notice from our integration rules, I have this. And we calculated the area function starting at 0 to be, so my area function here was 1/3 of x to the third. And notice this is an antiderivative of my function. And that was the connection, if you missed it before, that was the connection I was hinting at. We've got our antiderivative. So this is a of 3 minus a of 2. Plugging 3 and 2, in other words, into my antiderivative here. So what I can do is, let me jump down here. What I can do is figure these two area functions out, which is 1/3 3 to the third minus 1/3 2 to the third. So of course that is 9 minus 8/3, which is 19/3. All right, now that was a lot easier if I had this area function. So in other words, I didn't have to go back to Riemann sums to figure this out. All I had to know was that the first part of the fundamental theorem of calculus. If I have this, the right antiderivative, then I can just plug in the endpoints that I want the area for. I just plugged in 3 and I plugged in 2 and I found the area. I didn't have to go to Riemann sums to do it. I did, if you remember, have to go to Riemann sums to figure out which area function to use. But, lucky for us, the second fundamental theorem of calculus says that if we can find any antiderivative of f, then the definite integral from little a to little b is just plug little b and little a into any antiderivative. Any antiderivative. So I don't even need to go to the Riemann sums. I could have used any antiderivative. So of course we used the one that the Riemann sums told us to go with, which was 1/3 x to the third. But we could have used, let me use big F here, any antiderivative, which means it would be 1/3 x to the third plus some constant, and it would still work. So, and I should point out, so if any antiderivative works, let's just always use the one where it's plus 0. So in other words, we don't have to worry about that constant. Okay, so here, I want to find the exact area under the curve between 2 and 5. So I'm, in other words, calculating this, this definite integral. And I should be careful. We want to find the net area. I don't know if this thing dips below the x-axis or not. All right, so I need to first find an antiderivative. And when I say an antiderivative, I'm going to pick the specific one where the constant is 0. All right, so we know how to find antiderivatives. Just add, for a polynomial anyway, just add 1 to the power and divide by that new power. So it'll be 6x to the third divided by 3 plus 6x to the second divided by 2 plus 3x, which of course simplifies to 2x to the third plus 3x squared plus 3x. And now, if I want the area between 2 and 5, what we do, pretty simple at this point, plug in 5 into my antiderivative and subtract what we get if we plug in 2 into my antiderivative. So I'll start this out, but I won't finish it, just because once we get it in there, you can do the arithmetic. 2, 5 to the third plus 3 times 5 squared plus 3 times 5 minus 2 times 2 to the third minus 3 times 2 squared minus 3 times 2. I've already distributed the negative. So there, once you throw that into your calculator, you will have the definite integral from 2 to 5. And isn't that much nicer? We never had to touch Riemann sums at all. Okay, here's three good ones to get you started. Let me give you some hints. An antiderivative of this will be sine inverse. So this you'll just have to figure out what is sine inverse of 1/2 minus sine inverse of 0. So calculate those. Here, and let me throw some notation at you. I think we looked at this on day 1, but first let me get the antiderivative. The antiderivative that we're going to use anyway would be this one. And then we're going to evaluate that from negative pi over 2 to pi over 2. And so what this notation means is plug in the top one into your function, into your antiderivative, and then minus plug in the bottom one into your antiderivative. So let me, if you want to practice these, I will point out that on this one you should get pi over 6. On this one you should get 2 minus pi. And then here, think about what an antiderivative for cosecant is. Well, cosecant squared, that'll be cotangent, except we're going to need to be negative. So this will be negative 8 cotangent of 4x. But of course, an antiderivative requires that when you take the derivative of it, you get this original function. But if we take the derivative of this, we're going to have to, because of the chain rule, we're going to have to multiply that 8 by a 4. So instead, what we should do for the antiderivative is preemptively counteract that with a divide by 4. So this will come out to be a negative 2 cotangent 4x, and you're going to evaluate that from negative pi over 16 to pi over 8. And I believe what I will get is a negative 2. All right, but double check me on these, and please on Discord let me know if I've made any mistakes that you find, and hopefully I can come in here and fix them. All right, I will see you all later. This is a big section. very powerful stuff. This was really the introduction to the power of calculus. So enjoy it. I'll see you all online.